Hello everyone, welcome to my YouTube channel. So today I'm going to discuss an interesting problem from linear algebra part of JAM 2024. Okay, this is a very nice problem, but if you want to solve it by just using the concept of matrices, then it will be very hard for you to search actual answer. Okay, so that's why I'm going to solve it in a different approach, and the approach is nothing but just use of linear transformation, the idea of linear transformation. So okay, let's start. How do I start? How do I use that? So first observation is that a fact, if A is a m cross n matrix, then we can think it as a linear map m cross n matrix with real entries. We can think it as a linear map from Rn to Rm, Rn to Rm, right? This is the basic linear algebra fact, and we are going to use this. So the first question, first statement saying that for all such non-zero matrices A and B, there is a non-zero matrix Z such that AZB is a 6 cross 4 zero matrix. Okay, so we can think it in terms of linear transformation. So statement P, A is a 6 cross 5, B is a 5 cross 4. So A is 6 cross 5, Z, that means Z must be 5 cross 5, and B equal to 5 cross 4. So if we think it as a linear map, then we will have R5 to R6. Say this is TA, this is TZ, R5 to R5, and this is TB, R4 to R5. And AZB equal to 0 is equivalent to showing that the composition will be reversed, since the map 6 cross 5 means the map is from R5 to R6, so that means it will be T. So AZB equal to 0. Okay, so AZB is a matrix of zero matrix of order 6 cross 4, right? So here it will be from R4 to R6, right? Here it will be from R4 to R6. That means I think I did some typo. 6 cross 5. So right. So that means it will be TA compose TZ compose TB equal to, this map is from R4 to R6, and that map must be 0, right? So this is the first observation. Okay, now we need to find this Z, right? The question is saying that if A and B are two non-zero matrix, then we can find out some Z that satisfying this condition. Okay, so correspondingly, if we think about linear map, so we have given two linear maps, say TA and TB, then we need to find out a linear map TZ from R5 to R5 such that this composition is zero linear map. Okay, so now it is quite simple. How do I do that? So TB is a linear map from R4 to R5, right? So say that means image of TB is spanned by some vector. Okay, some vector. So span by say u1 u2 up to uk. Now since the domain has dimension 4, that means image of TB has dimension at most 4. So dimension of image or range, dimension of range of TB is less equal to 4, right? So that means K is less equal to 4. I can take span of this where this is the basis of image. So then K is less equal to 4, right? So that means K is less equal to 4. So if K is less equal to 4 and this is inside R5, this is inside R5, then we can extend it as a basis of R5. So say without loss of generality, assume that the rank is 4. We can take, okay, you can take any rank less equal to 4. It is at most 4. So say it is A, B, C, D, and extend it as a basis of R5. Say the basis is given by, say, A, B, C, D. This is from the basis of the image of TB, and say E. Then it is the basis of R5. If the image has dimension 3 or 2, image cannot have dimensions 0, right? Because it is non-zero map. So image has at least one non-zero vector. So dimension is at least 1. So if image has dimension 1 or 2 or 3 or 4, anything, you can just extend it to a basis of R5. And now define a linear map. Say the linear map is TZ, is defined by A goes to 0, B goes to 0, C goes to 0, D goes to 0, and say E goes to E itself. This is the non-zero linear map. Why? Because E maps to E itself, which is a non-zero element. But if you do TZ compose TB, what will you get? TZ compose TB is 0 identically, because this element maps to 0. The element which is the basis of range of TB is goes to 0. That is inside the null space of TZ. So that's why TZ compose TB is 0. Now if TZ compose TB is 0, if TZ compose TB is 0, then you can compose it with TA, doesn't matter, right? Because then TA compose TZ compose TB is also 0. So we find the linear map TZ such that TA compose TZ compose TB is 0. So that is the idea. You can do for any matrix B. If you already given a matrix B, you can take this linear map TB and then take the basis of the range, extend it to a basis of R5, and then define a linear map in this way. And that gives you a linear map because you have defined it on the basis. Because this is here A, B, C, D, E, this is the basis of R5. So you have defined it on basis. So that means it gives you a linear map, and that linear map, and from that you can conclude that TZ compose TB is 0. So TA compose TZ compose TB is also 0. And that's why if you take it for the matrix, then the matrix becomes AZB. This matrix is 0. Here if you take the matrix representation of TZ with respect to this basis, then that matrix is our required matrix Z here, right? So that is the important thing. So if you just think it in terms of matrix, then it will be very hard. But if you think it in terms of linear map, it is very easy. Now for statement B, the same thing will happen. Okay, so statement Q. So the statement Q is saying that BYA is 5 cross 5 matrix, right? So B is 4 cross 6, sorry, B is 4 cross 5, Y will be 5 cross 6, A will be 6 cross 4. 6 cross 4. A is 6 cross 5, B is 5 cross 4. Sorry, B is 5 cross 4. Okay. So B is 5 cross 4. A is 4 cross, same thing actually, BYA. So B is 5 cross 4, A is 6 cross 5, A is 6 cross 5, so Y must be 4 cross 6. Then BYA is, is 0 matrix 5 cross 5. Now do the same thing, take its linear map. So TB is R4 to R5, TY is R6 to R4, and TA is R5 to R6. Then TB compose TY compose TA is from R5 to R5. Okay, R5 to R5. Now do the same thing. So you know A is a 6 cross 5 matrix, right? So that means it is R5 to R6. Defined it from, so TA is defined from R5 to R6. Okay, that means dimension of range of TA is less equal to 5. Okay, now here the codomain is 6 dimensional. That means B be the extended basis. You can do the same thing, extend this extended basis from the basis of range of TA. So take range of TA, find its basis. Since the dimension is less equal to 5, you can extend it. Okay, and you can extend it this basis to a basis of R6, extended basis of R6. Now again same, if you take without loss of generality, the dimension is 5, so take range of TA, say given by u1, u2, u5, and this B is a basis, say u5 comma V. This is the extended basis, and then define Ty as u1 goes to 0, u2 goes to 0, u5 goes to 0, and say V maps to, say, any non-zero vector V. Any non-zero vector, you can take V, you can map V goes to any other vector also which is non-zero. Then ultimately this Ty is a non-zero linear map, so its corresponding matrix representation with respect to this basis gives you the non-zero matrix. And if you again by same argument, if you do the same thing, then BYA, this composition is 0. That's why both P and Q, these two statements are correct. Thank you.